Hi everyone, welcome to another module for Kines 7103, which is taught in health kinesiology and recreation here at the University of Utah. In this module, we're going to be talking about controlling for other variables in our multivariable regression. So in the previous module, we introduced the idea of multivariable regression, and we talked about conceptually what it meant to control for another variable and exclude shared variance from a model. In this follow-up module, we want to talk about how we really unpack that multivariable relationship and explain what it means to control for another variable and mathematically how we're removing that shared variance when we do this calculation. So first, we're going to be working with the data set from the textbook in chapter 6 when we were looking at the ages, heights, and weights of these various students to sort of developmentally understand the relationship between these three different factors. So we had this multivariate relationship in which we were looking at a student's weight in pounds as a function of both their height in inches and their age in years. And we talked about how height changes as both a function of weight and as a function of age. Now, when we import this data into R, we're actually going to kind of start from the end and take a look at the multivariable model first, and then we'll unpack it to actually look at the individual regression coefficients and how we get those values. So first, when we run this linear model in R, we're predicting weight as a function of height and age after we have imported this data frame. We get this regression output. And these are our coefficients. We have an intercept of negative 141.22, a slope for height, which is 3.597, and a slope for age, which is 1.278. And again, the intercept is always going to be the predicted value of y when the x's are 0. So in that case, this is our predicted weight when height and age are equal to 0. So it's a nonsensical estimate, and we're not terribly interested in the intercept in this model. However, we are interested in the effects of height and the effects of age. So here we have our slope for height. This is the predicted change in weight for a 1-inch increase in height. And this is the predicted change in weight for a 1 year increase in age. But the important caveat here is that this is controlling for each other. So controlling for height, this is the change in age. And for controlling for age, this is the change in height. In this module, we're going to be talking about how we get these coefficients here and how we actually arrive at these values. In the lab, we're going to be talking about how to make this calculation and how to calculate the R squared, the F statistic, and the probability of that F using the formulas that we've learned from the textbook. We'll also talk conceptually about how to do these tests for the individual estimates, right? But these are model comparison tests. We have gone through sort of the math of how to do the statistical inference before. So the logic of it is very similar. And we'll do a little bit of an assignment in lab to go into detail about it. But in general, we're just going to let R or SPSS or whatever statistics program you're using, tell us what all these values are. But today in the module, we're going to derive these values. And then in lab, we'll derive the things here in green and the things shown here in red. So first, we want to understand the relationship between weight and height and weight and age. So when we plot weight as a function of height, you can see we have a distribution that looks something like this. And we have students who have some extreme points over here. And then here we have weight as a function of age, and we have those same students, right, who make up relatively extreme points over here on either end of the spectrum. Both of these relationships are positive, right, relatively unsurprisingly. As students get taller, they weigh more, but also as students get older, they weigh more. However, the tricky part comes when we put both of these variables into our model at the same time, because not only is there a relationship between weight and height and weight and age, but there's also a relationship between height and age, and we need to exclude that shared variance, because otherwise, as we discussed in the previous model, we're going to end up counting it double. We had this graphical representation in the previous module, right, where we can think about the total variance in each of these variables as a surface, right? So it's a circle with an area equal to the sum of squared errors, right? So we could express these as an area of the sum of squared errors, and the degree to which these variables are correlated is represented by the degree to which they overlap, right? This area between the red and the yellow circles would be the proportion of weight that's explained by age, and the overlap between the red and the blue circles would be the proportion of weight that's explained by height. But this area in the middle, right, is explained by both height and age, because of course height and age are themselves correlated. So we need to exclude this shared variance from our model before we actually calculate these regression coefficients, because otherwise it's counting double, right? We would have part of the weight that's explained by height, and then that same part of weight that's getting explained by age. And we can't have that, right? So we have to come to some sort of method of handling that shared variance. And in multiple regression, what we're usually going to be doing is excluding that shared variance first. So that way we can just look at the part of height and weight that is independent of age, right? So ignoring this area here, how much of height and weight overlap with each other. And now rather than this whole area, the part of height that's independent of age explains this part of weight that is also independent of age. And similarly over here, this used to be the part of age that explained variation in weight, but when we exclude the shared variance, now this is the part of age that's independent of height, explaining the part of weight that is independent of height. And to understand how we're going to remove this shared variance, it's useful to first plot the distributions of the bivariate relationships. So we're looking at height as a function of age, and we're looking at weight as a function of age. So we want to remove then this part of the data. So we need to remove the part of height that overlaps with age. So we're going to remove this shared variance here from our height variable. And we want to remove the part of weight that overlaps with age. So we need to remove this shared variance here from our weight variable. Now, in order to get the parts of height and weight that are independent of age, we need to extract the residuals from each of these models. So I've highlighted the residuals both in the equation and here on the graph using these purple lines, right? So for height and age, the part of height that's explained by age is on our best fit line. This is what we would predict your height to be given your age. The part of height that's unexplained by age is what's left over. So that's our residuals. Similarly for weight, the part of weight that's explained by your age is along this best fit line. This is what we would predict for your weight given your age. So the part of weight that's not explained by age are the residuals, what's left over, right, between our data points and our model, and we're going to take those errors. So we're going to get a set of errors from here. We're going to get the residuals of height controlling for age, and we'll get the residuals of weight controlling for age. And that's going to allow us to say what part of height that's independent of age explains the part of weight that is independent of age. So what I've done here and what we'll do in the lab is extract those residuals. So on the y-axis, we have the weight residuals controlling for age. And on the x-axis, we have the height residuals controlling for age. So now, rather than raw weight or raw height, we're plotting residuals. So notice they're both centered around 0. And the way we can interpret this then is that positive residuals were larger values than our linear model would predict. Negative residuals are smaller values than our linear model would predict. So when we look at this plot, now what we're saying is if you were at 0, you were exactly what we would predict for your age, or you were typical for your age, right? So people at 0 on the y-axis had a weight typical for their age. People who were at 0 on the x-axis had a height typical for their age. And as you go in the positive direction, you're tall for your age or heavy for your age. And as you go in the negative direction, you're light for your age or short for your age. And you can see that these two sets of residuals are positively correlated. And if we actually fit a regression slope and intercept to these residuals, what we would get is an intercept of almost 0, right? Because the mean of each of these things is 0. It really is 0. R is just going down to a very, very small number and being a little bit picky. But the slope of the residuals is 3.597, right? So for every 1 point increase in age, right, every year older you are, in your height residuals, for every 1 inch taller you are than we would predict from your age, you gain 3.597 pounds than we would predict for your age. So this is the slope of the line through the two sets of residuals. And you'll notice, if you remember back to the original slide, and we'll show you again in a second, that this is the exact same slope for the effect of height that we got out of the multivariable model, right? So when we've controlled for age by removing its variance from weight and removing its variance from height, we get the same slope as when we plot the residuals, right? And conceptually, this is what the multivariable regression is doing. It's excluding the shared variance from each variable and then calculating a slope based on the residuals. And we can see this if we look at our other relationship, which is weight with the variance due to height removed and age with the variance due to height removed. Again, these are sets of residuals that we're regressing onto each other. Oops, I'm just noticing my text labels got a little bit out of place here. Joyce is actually somewhere in this area, I think. Her dot got shifted a little low. But what we're looking at, right, again, are sets of residuals. So 0 is a weight that we would predict based on your height. And 0 here is your age based on what is perfectly lines up with what we would predict based on your height. As you go up in the positive direction, we're saying you're someone who is heavy for your height. And as we go down in the negative direction, you're someone who is light for your height. And over here, this one is a little bit stranger to think about maybe, but here we're saying you are young for your height, right? So we're saying that you are younger than we would predict given your height. And over here, you are old for your height, or that is to say you are older than we would predict given your height. And if we actually fit a line to this, we use our ordinary least squares regression to get a slope and an intercept for these data. What we end up with is an intercept again of 0 and a slope of 1.278. And that 1.278, again, if you remember back to the original slide, is the slope for the effect of age when we were controlling for height in the multivariable model. So again, when we're controlling for the other variable, what we are literally doing is removing that shared variance and then refitting regression equations, where we are fitting that line through the dependent variable with the variance that we're controlling for removed, and the predictor variable with the variance that we are controlling for removed. So regressing these residuals onto each other gives us the same parameter estimates as the multivariable model, right? So here, again, in our original full multivariable model, the effect of height was 3.5970, and we said that that was statistically significant, right? And if we look at our model with the effect of age, we can see that that has the exact same parameter estimate here. If we look at age, it has a value of 1.2784, right? And we get the exact same parameter estimate in our model where we're regressing sets of residuals onto each other here. So again, hopefully that helps clarify what it means when we're controlling for a variable in a multivariable regression model. This shows you how R is actually deriving those parameter estimates when we run that LM command to start a multivariable regression. In the lab, we're going to talk more about how and walk through the generation of these estimates. And we'll also get into a discussion about how we calculate p-values for each of these individual statistical tests, but also how we calculate the omnibus p-value when we consider the model as a whole.